Let's investigate the harmonic oscillator. I will first consider the simple harmonic oscillator in Newtonian mechanics. Let's investigate this function over here. This is a potential energy function. So V of x is a potential energy function that depends on the spatial coordinate x. We're only dealing with a one-dimensional system. So that's why we only have one spatial dimension, so that is x. And the form of this potential energy function is 1/2 kx squared. So there is a quadratic dependence on the spatial coordinate. This is a very important property. This is sometimes called a Hookian potential. And we'll get to why we call it a Hookian potential in a second. So I just want you to notice that this is a parabola and there is a minimum at the origin. So at x equals 0, we have a minimum. Now that is guaranteed to us by this condition over here. K, this constant k over here, has to be positive. If it was negative, then this parabola would be like this. It would open downwards. And then we would run into trouble because we would have a maximum over here. And we are after oscillations. This is a harmonic oscillator. We want a particle to be oscillating close to a minimum. So let's use the work energy theorem. And let's try and write a force that's going to describe the motion of this particle. So we'll have a look at the work energy theorem. And what we can actually do is we can describe the force as the negative gradient of the potential energy function. And I'll do that over here. So F, I'm going to use to denote the force. So this is the force F. I'm going to set that equal to minus the derivative with respect to position of V of x. So V depends on the position. It depends on where the particle is. That's what determines the particle's potential energy. And we're going to see in a moment why there is a factor of 1/2 out the front. Why wouldn't we just define this as k times x squared? Well, there's a good reason, and we'll see in just a second. So this is the one-dimensional case. If we had higher dimensions, this would generalize to the gradient. So we'd have the gradient of the potential. But because we're just dealing with one spatial coordinate, we just have one total derivative. So this is a derivative with respect to x. There are no partial derivatives over here. So let's substitute this form of the potential into this equation. And that's going to give us minus d dx of 1/2 kx squared. And we can use the power rule for differentiation. And this exponent up here, this 2, is going to come down and it's going to cancel this half. And that's going to give us minus kx. And have a look. This is why the factor of 1/2 was out the front. So we defined the factor of 1/2 up over here so that it would get erased by the differentiation. So the derivative would get rid of this half. And that gives us this relationship over here. And this relationship, this equation for the force, is called Hooke's law. This is Hooke's law, and it is very useful for describing a mass on a spring. So if you have a spring and a mass connected to it, you're going to have some kind of oscillatory behavior. And if we're just looking at a simple harmonic oscillator where there is no resistance to the oscillations, then we're going to have this kind of system over here. So this is going to be the force acting on a particle. And this is called Hooke's law, and this is a Hookian potential. That's why we call this a Hookian potential. So now what we can do is we have Hooke's law, but we also have Newton's second law of motion. F equals ma. So we can set this equal to mass times acceleration. So this is coming from Newton's second law of motion. So we have Newton's laws of motion, and we also have Hooke's law, which describes the force a spring will exert on a particle. So this minus sign over here is very important. This minus sign tells us that this is a restoring force. So if we have positive x over here, so if x is positive, we're on this side over here, then the force is going to be negative. The force is going to point in this direction. And if x is negative, we're going to have minus times minus, which is going to give us a plus. So the force is going to point in this direction if we're on this side. So if the particle is up here, it's going to get pushed back towards the minimum. And if the particle goes up here, it's going to get pushed back towards the minimum. It doesn't matter where the particle is, the force is always going to push it back towards this minimum at the origin. And we've set the origin at x equals 0 to be the minimum of this potential energy function by definition. And it's very important that we have k positive. Otherwise, this is no longer oscillatory behavior. If this was negative, we'd have a maximum over here, and the particle would be going away from the origin. It would be repelled, and we wouldn't have a minus sign over here. We would actually have a plus sign. So the particle would get repelled away. So that is why this sign convention is very important. In order to have oscillatory behavior around a minimum, we need to have this positive. What if it was 0? What if k was equal to 0? Then this potential energy function would just be equal to 0 everywhere. So the particle would have no potential energy. And that is a free particle. So a free particle only has kinetic energy. It only has energy associated with motion. So that is not a case we're going to be considering in this video. We're only considering this type of potential. Now, I want to add something to this equation over here. The acceleration can be thought of as the second time derivative of position. So we can write this as mass times the second time derivative of position, right? Because acceleration is the derivative of velocity, and velocity is the derivative of position. These are all time derivatives over here. The distinction, over here we have a position derivative. This is a spatial derivative because we're working with the potential energy function. And over here, we're working with time derivatives. So the second time derivative of position is acceleration. That is by definition. So we can use this relationship now. We have Newton's second law of motion, and we also have Hooke's law. We can use that relationship to get an ordinary differential equation. I'm going to write it down over here. I'm going to divide both sides by mass. So we're going to have the second derivative of position with respect to time is equal to minus, remember that very important minus sign from Hooke's law, k over m times x. And I can write this constant over here as a slightly different form. So I'll write this as minus omega squared x. So this is a second order, we have a second order derivative over here. It's a second order ordinary differential equation. It's an ordinary differential equation because we're only differentiating with respect to time. So there's only one variable that we're dealing with. So time is the variable that we're differentiating with respect to. There's no position derivatives in this ordinary differential equation. Now, this omega, I can actually define to be of this form. So we can define omega to be the square root of k over m. And this is a very useful quantity. This is the angular frequency of oscillation. This is the mass, and this is a constant that we can physically interpret as a constant that tells us the properties of a spring. So if we're dealing with a physical spring in Newtonian mechanics, this k is going to tell us how the force is related to the displacement. So it's a linear dependence. The force and the displacement are linearly related to each other. So the more you move, the greater the force you will experience. And there's a lot of systems in nature that behave like that, or at least they can be approximated by that. In general, if you're trying to apply this to really large values of x, you're eventually going to get to a point where you break the string. So you're eventually going to snap it. So that is the point where this is no longer a Hookian potential. But for small x over here, and for small deviations away from some sort of minimum, this actually holds. So this is a very good description of reality. Now, I want to do a slight manipulation of this. If I square both sides, then I'm going to get omega squared equals k over m. That's what we have over here. Omega squared is the same as k over m. But if I rearrange that slightly, I can rewrite k as m omega squared. So m omega squared can actually replace k in this potential energy equation. So we don't even have to worry about k. All we have to do is worry about the mass of the particle and the angular frequency of oscillations. So what is the general solution to this ordinary differential equation? We're looking for a function x that satisfies this equation. So we need a function that when we differentiate it with respect to time twice, it gives us back the same function with minus times a constant. And we need this constant to come out twice. That's why we have a factor of, we have a squared. We have omega times omega. So it comes out twice when we differentiate it. And a function that satisfies this property is the cosine and also the sine. Sine and cosine both satisfy this property. We can also solve this with exponentials, but we're not going to do that in this video. We're going to stick to sinusoidal functions. So the general solution to this ordinary differential equation, it's a second order equation, is given by this. So we have x of t, that's the position as a function of time, is going to be equal to some coefficient times sine of omega t. You see why I defined omega? Because it shows up very neatly in this equation. So we have omega t over here, and then we also need some other coefficient, we'll call that b, so a and b are our coefficients, and then we have cosine of omega t. So omega t is entered into each of these sinusoidal functions, and omega tells us the angular frequency of oscillation, and t is the time. So we have a linear combination of these two solutions, and we can do that because this is a linear differential equation. This by itself is a solution, and this also by itself is also a solution. If we differentiate sine twice, we're going to get minus sine, and we're also going to take out an omega with the chain rule. So we're going to get two factors of omega. That's going to give an omega squared. So we're going to have sine omega t with a minus omega squared factor at the front. And the same thing is going to happen for cosine. If we differentiate it twice with respect to time, we're going to have minus cosine omega t. And every time we differentiate, the chain rule is going to bring out two factors of omega. So we're going to have omega squared. And this is why these guys satisfy this ordinary differential equation. Now, I want to have a look at a slightly different approach. So over here, this is very common in Newtonian mechanics. We look at the position. We look at velocity as well. And if we wanted to specify these two coefficients, we would need some initial conditions. And what we could also do is we could differentiate this equation, and that would give us the velocity. We could differentiate it again, and that would give us the acceleration. These are all time derivatives. So if we keep doing time derivatives, that's going to give us velocity and acceleration. And if we multiply the acceleration by mass, it's going to give us force. So we have an expression for the force on the particle. And that is very useful. That is how we describe this system with Newtonian mechanics. We look at position and velocity. Those are very useful quantities. So this is the most general possible solution. And if you wanted to look at a specific solution, you would need initial conditions. You need to know where is the particle starting, what is its initial value of x, and how fast is it going? What is its initial value of velocity? So you would just take the derivative of this with respect to time, and then you would solve for a and b. And that would give you some solution that is specific to those initial conditions. Now, let's approach this problem slightly differently. Let's have a look at the energy of this particle. So if this particle is moving in this potential, it's going to have a total energy E. So I'm going to write that down. I'm going to write E is our total energy. So I'll write that in a different color so we can distinguish from all of this stuff. So this is classical mechanics still. We're still in the classical paradigm. So the total energy E is going to consist of two quantities, the kinetic energy and the potential energy. The kinetic energy can be written as 1/2 mv squared, and the potential energy can be written as 1/2 kx squared. So I'm just adding the kinetic energy and the potential energy. Those are the two types of energy that this particle can have. This is just a point particle. So this term over here depends on the velocity, and this term depends on position. So we have a position coordinate, and we also have the time derivative of the position coordinate. We can also write this v as x dot. We could write that as the time derivative of position. And that is commonly done in Lagrangian mechanics. But now let's move over to the conventions of Hamiltonian mechanics. In Hamiltonian mechanics, we don't like to deal with velocities. We'd actually prefer to deal with momenta. So I'm going to change this expression and write it in terms of momentum. And there is a video in the quantum mechanics playlist that is dedicated to this relationship between writing the kinetic energy as a function of velocity and as a function of momentum. So I'm going to do that over here. We're going to change this kinetic energy term, and we're going to make it p squared over 2m. And remember that linear momentum in one dimension is just mv. So it's the product of mass and velocity. And if you substitute mv back into this equation over here, you can cancel one of the m's, and that's going to give you 1/2 mv squared. So this term is the kinetic energy of the particle. But now we have to reorganize this term over here, and we can write k slightly differently. Up here, I wrote a slightly different form of k. I'm going to write that again. So I'm going to write this as 1/2 m omega squared x squared. So we have the same expression over here. It's still that Hookian potential. There's still a quadratic dependence on x. But the only difference is that I'm not writing it in terms of k, I'm only writing it in terms of m and omega. Because when we generalize this problem, we're not actually just interested in springs. And k is physically meaningful when we're talking about springs, but when we're talking about a general situation of oscillations around a local minimum, then we might not even have a spring. But useful quantities are always going to be the mass of the particle and the angular frequency of oscillation. So that's why I've written it in this form. And this is a far more friendly form when we try and turn this into quantum mechanics. So what we're going to do is we're going to turn this system into a quantum mechanical system. All of this up here has been classical mechanics. This is still kinetic energy and potential energy in classical mechanics. Now let's turn this into something that is more useful in quantum mechanics. So how would we turn this into something that's useful in quantum mechanics? This is very useful in Hamiltonian mechanics. In Hamiltonian mechanics, we like to deal with the total energy, and we like to deal with momenta and position coordinates. But here's the thing. What we want to do is we want to turn these guys into operators. And that is the language of quantum mechanics. It's the language of Hilbert spaces and operators. So let's put a little hat on these guys, on position and momentum, and let's turn this into the Hamiltonian operator. So the Hamiltonian operator, I'm going to write it like this. We're going to have H with a hat. So this is the same as the total energy. So this is the operator that's associated with the total energy. We're not writing E anymore. E is just a scalar quantity that is constant. But this is now an operator. And I'm going to follow this form over here. I'm going to write it down. And instead of just scalar values, we're going to have operators. So P is going to have a hat on top. And it's going to be an operator quantity. And we're going to divide by 2m. M is the mass of the particle. And then we're going to take this potential energy term. We're going to get 1/2 m omega squared. We'll have x, and we'll write a little hat on top, because this is the position operator, and we need to square that. So it's exactly the same form as this Hamiltonian mechanics form of the simple harmonic oscillator. But we've just changed momentum and position into operators in quantum mechanics. And if we express this in the position representation, this turns into a derivative with some constants out the front, and this turns into just multiplying by x. So what we can actually do is we can apply this Hamiltonian operator onto a state. And we can apply it onto a very specific type of state. We can apply it onto an eigenvector. And this is not just an eigenvector, this can be thought of as an eigenfunction, because it depends on a continuous quantity. So if we take psi to be our eigenfunction of the Hamiltonian operator, then what's going to happen? Well, we're actually going to get the time-independent Schrödinger equation. And that's going to give us the eigenvector and eigenvalue equation for this operator. So let's do that over here. This Hamiltonian can be used to write the time-independent Schrödinger equation in the position representation. So this kinetic energy term, as we've seen before in the quantum mechanics playlist, is going to have this form. We're going to have minus h bar squared over 2m. And then we're going to have a second derivative of psi with respect to the position coordinate. And then we're going to add to that the potential energy function, which is 1/2 m omega squared x squared. And that needs to act on psi as well. And this is going to give us the energy times psi. So have a look at this equation over here. This is the kinetic energy operator acting on psi, and this is the potential energy acting on psi. And that's giving us an eigenvalue of the energy operator, that's E, acting on psi. So this is the same as an eigenvector equation. Psi is taking the role of the eigenvector or the eigenfunction because it depends on a continuous variable x. And these guys over here, this is the same as the action of the Hamiltonian operator, and this is the same as multiplication by an eigenvalue. And if we solve this equation, just as we've done before for the particle in a box, if we solve this equation, it's going to give us all of the eigenfunctions. And those we can associate with stationary states. And we can actually take a linear combination of those, and we can write any possible wave function. So the goal of this is to write any possible wave function in terms of these building blocks, these stationary states. So that is what we're actually going to do in later videos. We're going to try and solve this, and we're going to use some interesting methods. And one of the other things that I want to show you is that this Hamiltonian doesn't just have this form. We can also write it in a very interesting form. We can write it right underneath here. The Hamiltonian operator can also be written in terms of the ladder operators. And these ladder operators are actually very useful. And sometimes they're actually more convenient than position and momentum. And this combination of ladder operators, A, dagger, and A, can also be written like this. We can have the number operator plus a half. And I'll actually be deriving this in later videos in the quantum mechanics playlist. So we'll have full derivations of where this comes from. These are alternative ways of writing the Hamiltonian for the quantum harmonic oscillator. Here, N is the number operator, and A dagger and A are the ladder operators. And H bar omega is a quanta of energy. So what we're going to find is that energy comes in discrete chunks. There is a ground state energy, and each energy above that is a discrete interval. So you can only have those discrete energies. And each of those energies is associated with a particular psi. And that psi is one of those stationary states. And we can use all of those ones by the principle of superposition. We can write a linear combination of them, and that can give us any possible wave function. Any physically realizable wave function can be written in that form. So this is a bit of an overview of how we can turn this classical problem of the harmonic oscillator, this is specifically the simple harmonic oscillator with no resistance to the motion, and we can write the total energy of the system in a form that is convenient for Hamiltonian mechanics, and then we can take all of the language of Hamiltonian mechanics, we can translate it into quantum mechanics, and we can create this Hamiltonian operator. The Hamiltonian for the quantum harmonic oscillator can be used to write the time-independent Schrödinger equation in the position representation. And if we solve this big complicated differential equation, we can get all of the wave functions and the associated energy levels. But there is a slight problem over here. This is a very tedious differential equation to solve because of this quadratic term. There's an x squared term, and that makes solving this very tedious. So we have an alternative way to solve this system and to actually work out the time evolution of the quantum harmonic oscillator. We can implement ladder operators. And ladder operators and this number operator over here are going to show up in a lot of the videos in this quantum mechanics playlist. They have applications not just for the quantum harmonic oscillator, but for many systems in quantum mechanics. The harmonic oscillator is also very useful as an approximation to other more complicated systems. Take a look at this graph over here. This green function is some arbitrary potential energy function that depends on the spatial coordinate. So this v of x is not the same as this v of x. This is a Hookian potential and it's quadratic. Over here we have something far more complicated. But if we zoom in around this local minimum, we can find some very useful properties. Close to this local minimum, this function can be approximated by a quadratic potential. And because we can approximate it by a quadratic potential, we can use all of the results that we have found from the quantum harmonic oscillator. So let's take a Taylor series expansion around this point. This point I'm going to call x0. It is the spatial coordinate where the minimum of v of x occurs. So very, very close to this minimum, we're going to zoom in and we're going to do a Taylor expansion. So let's do that over here. So what I'm going to do is I'm going to write v of x, that's this v of x over here, not the one at the top. I'm going to write that as equal to v of x0, that is the height of the graph over here. So up to here, that is the height. So that's going to be a constant term. Then we're going to have a linear term in our Taylor series expansion. We're going to have v prime of x0 times x minus x0. And this is our linear term with the derivative evaluated at x0. And then I'm also going to write a quadratic term. So we're going to need a factor of a half. This is actually 1 on 2 factorial, but 2 factorial is 2. So we just have a half. And then we're going to have the second derivative. I'm using this little dash notation. And that's evaluated at the point x0. And we have to have x minus x0 all squared. And we can keep going. We can add higher order terms. We can have a cubic term, and we can have a quartic term, and this can keep going on and on for however much accuracy we need. If we want to have a more accurate approximation, we can add more and more terms. But here's the thing. We can actually just use the terms that we have over here. And let's apply some of the things that we know about local minima. If we have a local minimum over here, and we were to take a tangent line very close to the local minimum, the tangent line would be close to flat. And if the tangent line is very close to flat, that means the derivative, just the first derivative, evaluated at x naught, has to be equal to 0. So we can take this first derivative over here, and we can set that equal to 0. So the linear term in the Taylor expansion is actually going to disappear. This is because we are at a local minimum. And we also know that this term over here has to be positive. Otherwise, we wouldn't be at a minimum, we'd be at a maximum. Now, you can get into some problems over here. If this term is not dominant, and if the cubic and quartic terms actually dominate, and they're more powerful than this term over here, then we won't be able to use this approximation technique. So every time we do an approximation, we have to check the validity of the approximation. We have to make sure that these higher order terms can be neglected. If they can't be neglected, and they're actually stronger than this term, then we can't use this method that I'm about to show you in a second. So what do we have left? We have used the fact that this is the local minimum to get rid of the first derivative. So that gets rid of this term over here. So what we can do is we can just consider this term and this term. We can truncate this series over here, and we can just consider the second order term to be the highest order term. So what I can do is I can move this guy onto this side, and I can say that v of x minus v of x naught, right? This is just the constant that tells us how high this point is. This is approximately equal to this quadratic term over here. So we have 1/2 v double prime evaluated at x naught times x minus x naught all squared. So this is just an approximation because we're removing all of those higher order terms. But this part over here is not an approximation because we know that the derivative has to be equal to 0 at a local minimum. But as soon as we deviate away from that minimum, this starts to be non-zero. You start to get a little bit of a slope emerging as you move away from the minimum. And that slope is actually associated with the restoring force in classical mechanics. So now let's have a look at what we can do over here. We have a little term over here that's being subtracted, and we have another term over here. We can get rid of those two terms by moving the origin of our coordinate system. So if the origin is set at 0, 0, we can move that origin over to x naught, comma, v of x naught. And if we do that, if we do this coordinate transformation, then this is going to give us v of x is approximately equal to 1/2 v double prime of x naught times x squared. So this x naught disappears because we've done the coordinate transformation, and this v of x naught also disappears. So we can identify that this takes the role of k. So v of x naught is actually the same as k. And we know that this is greater than 0. So this is a positive value. The second derivative of the potential energy function evaluated at this local minimum, x naught, has to be greater than 0. Because if it was equal to 0, then we wouldn't be able to do this quadratic approximation, and we'd have to consider higher order terms. And if this was negative, well, then we'd have a local maximum. And we'd have one of these situations over here. So we'd have one of these points that are maxima. So have a look at this. This has the same form as a harmonic oscillator. So I can write this over here. This is actually the same as 1/2 kx squared. So we have 1/2 kx squared. And that is exactly the potential that we've been dealing with up here. So we can approximate any complicated potential, as long as these conditions are valid, we can approximate it with a harmonic oscillator's potential. So all of these insights that we have with ladder operators and this differential equation and all of the energy levels and associated eigenfunctions, we can apply all of those techniques to this region over here, this region of the potential. And as long as you're close to that local minimum, all of those things are going to be valid. But as soon as you start deviating away, we're going to run into trouble. But the neat thing is that we can actually quantify where our model will be valid. If these deviations are substantial, our model is not going to be valid. It's not going to predict what the actual system is going to be doing. But as long as we're close to this local minimum, we're going to have a good approximation with the harmonic oscillator. So this condition over here is very important. This is an essential condition, the fact that this is positive, because that allows us to have this kind of parabola that opens upwards. That's because of this condition over here. So this is just an approximation. You always have to check the validity of approximations. In this video, we covered the classical harmonic oscillator, we looked at Newtonian mechanics, then we looked at the language of Hamiltonian mechanics, we translated that into quantum mechanics, and we looked at how we can approximate other more complicated systems with the quantum harmonic oscillator. There are a lot of applications for this system and for these ladder operators. We're going to be seeing a lot of these things appearing in later videos in the quantum mechanics playlist. Make sure you check out the other videos in the quantum mechanics playlist. You can find them if you click over here.